tried the question number 3 from Friday's problem solving session? This was a promise between us that you'll at least try it. Has anyone tried? I can give 5 extra marks on the midterm for anyone who has tried. Anyone else? Let me know. Why should it be like this? Anybody who has to explain wave function when diverge the positive offer. Link के source के तरफ याद नहीं करना इसका जो टर्म है ठीक है गुड अब आगे बताओ कि इसके लिए कोएफिशिएंट रखो 1 और r से क्या कोएफिशिएंट है तभी सेटिस्फाई होगा आपने बोला है जो उसको आप दोनों इस सवाल सही तरह दोबारा से करके मुझे भेजेंगे. You're on the right track. You need to spend some more time. So this is the kind of question that I will ask in the exam and the quiz. So be prepared. But if you don't try, the onus is on you. It's your responsibility to at least give it, to attempt. Because I am not here to spoon feed, to provide you with all the details, with all the solutions, with all the answers. It's for you to attempt. तो ढूंढने निकलेंगे तो कोई चीज मिलेगी ना, ऐसे तो नहीं मिल जाएगी बैठे बैठे. क्रिस्टोफर कोलंबस ढूंढने निकला था इंडिया तो उसे मिला अमेरिका. तो ढूंढने निकलो, घर से निकलो, कोई मेहनत करो तभी कोई चीज मिलती है आपको. Alright, so today we're going to continue with our discussion, and this is a new topic that we're going to start, and things are going to get very interesting now, because now we're going to look into applications of what we've learned so far, especially concerning the hydrogen atom. And the first thing that we're going to look at is the concept of spin. So spin is a word, a 4-letter word in English language, but generally when we talk about spin, it conjures or it brings about the notion of motion, rotation about an axis. For example, the earth is revolving around the sun. That is the revolutionary motion of the earth around the sun, but the earth is also rotating about its own axis, which is an imaginary line that goes from approximately the north pole to the south pole, and we call this rotation about its own axis as spin. यही इंग्लिश लैंग्वेज में स्पिन का यही मतलब हमारे जहन में आता है, लेकिन इन क्वांटम मैकेनिक्स और इन मॉडर्न फिजिक्स when we use this word spin, it does not always mean, in fact it never means rotation about an axis, because an electron is no longer a particle, a nucleus is no longer a particle in quantum mechanics, it's a wave, it's a field. We know that an electron is a field. Therefore, when we talk about fields, there is no concept of rotation about an axis, there is no concept of motion, and I have highlighted this point at several instances before. ठीक है? तो spin is a misnomer. Misnomer का मतलब गलत नाम पड़ गया इसका, लेकिन historical reasons हैं, so we have to keep on using this word spin. But spin does not really mean rotation about an axis, because we know that our previous concepts of what an electron really is, they are shaken, they have fallen to the ground. An electron is no longer a particle, a proton is no longer a particle, they are waves, and they are fields, they are quantum fields, they are wave functions. And we cannot talk about motion in a wave function or rotation about an axis. So what really is spin? So the easiest way to understand spin is to move from a classical concept of spin to a quantum concept. Let me give you an example. Suppose you have a nucleus, and around the nucleus there is an electron, and the electron is orbiting the nucleus. This is the Bohr's model. This is the old quantum theory. So let's use the old quantum theory to find out what is meant by the spin and the angular momentum. What is the motivation? The motivation is that we've already seen that Schrödinger's equation gives us three quantum numbers. And what are those? N, L and ML. And L quantizes something, ML quantizes something. What does L quantize? The angular momentum, the total angular momentum. And ML quantizes the Z component. And what is meant by the Z component? What is the Z axis? Z axis कौन सा axis है जो upward point कर रहा है, downward point कर रहा है? It can be any axis. It can be any preferred axis in which we choose to make a measurement. But how do we measure angular momentum? We must have some mechanism of measuring angular momentum. In the freshman lab, how did you measure angular momentum in the rotational mechanics experiment? You measured angular momentum directly. Right. So you found the moment of inertia of your rotating disk I, and you found the angular velocity. The moment of inertia was found out, it could be found out geometrically. The angular velocity could be found out by a photogate timer and having spokes attached to the wheel, and you looked at the interruption of the photogate timer, you found the angular velocity. You multiplied the moment of inertia with the angular velocity, you got the angular momentum. So angular momentum is a physical quantity, energy is a physical quantity, velocity is a physical quantity, momentum is a physical quantity, and experiments must be designed which measure these physical quantities. When we say that angular momentum is quantized, you must have some measure or some means of measuring the angular momentum. Because angular momentum is a physical quantity like energy, linear momentum, velocity, mass. So in the classical world, measuring the angular momentum is easy, but how do we measure the angular momentum of an electron? And how do we verify that the angular momentum is indeed quantized? हमें verify करना है ना, टेस्ट करना है एक hypothesis को. देखो theory आपको कुछ ideas देती है, लेकिन until and unless you have experiments to verify your theory, you will always be in shallow waters. You really need some theory, some experiment to verify what you're doing. In fact, in quantum mechanics, in many cases, experiments lead the way. Experiments are performed and then theorists are clamoring to present a theoretical justification for the experiments. So we really need to measure the angular momentum. But how do we measure the angular momentum of an electron? And we know that the electron is not a particle. So so now I'm going to motivate a reason or a mechanism for measuring the angular momentum. Suppose we have this electron with charge minus e revolving around the nucleus, and keep in your mind the old quantum theory, Bohr's model. Now this electron has an angular momentum L. ठीक है, जाहिर है इसकी कोई ना कोई डायरेक्शन भी होगी. So the electron is orbiting the nucleus and the angular momentum is pointing in a certain direction. For this particular direction of revolution, which direction is the angular momentum pointing in? Upward. Okay. So since angular momentum is a vector, we have the angular momentum vector pointing in the upward direction for this direction of revolution. Now, is this a charged particle? Yes, it is. Now, when a charged particle is moving, it constitutes a current. If this is the radius of this orbit, r, and v is the linear speed of the electron, v is the linear speed of the electron, Bohr's model को ज़हन में रखना है हमेशा. Can you tell me what is the current that represents this moving electron? Can you find the current I? Now don't confuse I with the moment of inertia. I is the current. Can you find the current? One way to think of this is as follows. Suppose you have a hypothetical plane here on the orbit, and an observer is sitting on the plane. He or she wants to find out the charge that traverses this plane per unit time. That will be the current. So the current is charge per unit time. The charge is minus E, and the time period is the circumference 2 pi r divided by the velocity. So this is the current. Now can you write this in terms of the angular momentum? What is the angular momentum? The angular momentum is mvr. So what we need to do is write minus E mvr, and we divide by 2 pi mr square. This term is just the angular momentum of the electron. So we have minus E angular momentum 2 pi mr squared. This is the current. Next question. The electron is moving in a loop. A charge is circulating in a circular loop in accordance with the Bohr's model. Now, when a charge is circulating, does it produce some kind of field? Yes. What kind of field does it produce? It produces a magnetic field. Which means this current loop starts behaving like a magnet. It starts behaving like a magnet which has a north pole and a south pole. And can you tell me what direction this magnetic field will point in? In the upward direction? It's a negative charge. So it will produce a magnetic field in the downward direction, B, because it's a negative charge. So there is an angular momentum L, and associated with the angular momentum is a magnetic field, which is opposite in direction to the angular momentum, since it's a negative charge. So we can visualize this current loop as a small magnet, as a tiny magnet, and I can draw this magnet with a north pole and a south pole, and it's producing a magnetic field. So this current loop is akin, it's exactly equivalent to a tiny magnet. This magnet is called a dipole. So every current carrying loop is a dipole. It's equivalent to a small magnet which produces a magnetic field. Now using Ampere's law, can you find out the magnitude of this field? Alright, don't find the magnitude of this field. Let's do something else. If you have a current I circulating in a loop, this dipole will have a certain magnetic moment. It will possess a magnetic moment mu. Can you find out what the magnitude of the magnetic moment will be? Very simple calculation from your electricity and magnetism course. Given I, what will be the magnetic dipole moment? So you have a loop, an electron is moving in a circle like this. Okay? It's a charge, it's a current. Okay? अब ये जो area है इस loop का, now you want to find the magnetic dipole moment of this loop. That will be given by the current multiplied by the area of the loop. Okay? So the magnetic dipole moment will simply be I times the area of the loop, which is pi r square. Now let's insert the value of I that we obtained from the previous expression, minus EL 2m. This is the magnetic dipole moment. कोई भी आपके पास एक करंट है I, okay, which is moving in a loop, and the loop is on the boundary of it's on the perimeter of an area A. Then this loop acts like a magnet with a magnetic dipole moment mu, which is given by I times A. Or the magnetic dipole moment in vectorial form is given by I ये पढ़ा हुआ ना electricity magnetism में. You have a circulating current, and that circulating current is just like a small magnet. And the strength of the magnet is given by the magnetic dipole moment, which is the current multiplied by the area under the loop. So the area need not be circular. The area could be non-circular. Any fancy shape that you like. A, current I, and the magnetic, this will also act like a magnetic dipole, and the strength of the magnetic dipole will be just the current times the area enclosed by this circulating current. ये पढ़ा हुआ है ना electricity magnetism में. So a circulating current is just like a magnetic dipole. This is how a motor works. This is how a generator works. You have a current carrying loop. It's placed inside a magnetic field, and it rotates under the action of the magnetic field, because the magnetic field interacts with the magnetic dipole moment of the circulating loop. So now we have this electron around the nucleus. It has an angular momentum L, and associated with the angular momentum, it acts like a magnet, a small dipole, and the magnet has a strength which is given by the magnetic dipole moment, and the units are ampere meter square. So the strength of a magnet is given by the magnetic dipole moment. An analogy: if you have a positive charge and a negative charge, and they are separated by a distance r, this configuration is called an electric dipole. This is plus q, minus q, and the electric dipole P is given by q r, where r is the vector pointing from the positive charge to the negative charge. This is the electric dipole moment. Whenever two charges, electric charges, are separated, it constitutes an electric dipole. Similar to an electric dipole, we have magnetic dipoles, and the magnetic dipole is simply equivalent to a current that is circulating in a loop. So an electron that is moving in a circle around the nucleus forms a magnet, a tiny magnet, a dipole, a magnetic dipole, and the strength of the dipole is proportional to the angular momentum. So now what we really have, okay, the difference between electricity and magnetism is that you can break the connection between the positive and negative charge and have a positive charge independently from a negative charge. Positive charge exist कर सकता है ना independently from a negative charge. Therefore, you can have electric monopoles. But in magnetism, you cannot separate the north pole from the south pole. You break a magnet. This is a magnet with the north pole and the south pole. You break the magnet. You get two magnets. A south pole will be formed here, and a north pole will be formed here. You break this magnet. A north pole and a south pole will again be formed. To keep on repeating this process, you will never be able to separate the north and the south pole. This means that magnetic monopoles don't exist. In fact, experimentalists are searching for magnetic monopoles all over the world, but so far our experiments suggest that they don't exist. So we can talk of this circulating charge. Any circulating charge is similar to a magnet with a dipole moment, and this is the expression. Now if you look carefully at this expression, this L, is this a mechanical quantity? Yes, this is purely a mechanical quantity. Classically we think of the angular momentum as a mechanical quantity, whereas this is a purely magnetic quantity. So now we have a proportionality between a mechanical quantity, the angular momentum, and a magnetic quantity, and this is the constant of proportionality, E over 2n. Now if you want to write this in vectorial form, this is a scalar equation, but we can equally well write this in vectorial form, and the vectorial expression becomes mu equals minus E over 2m L. So this is an expression you have to remember. That is, you have a mechanical angular momentum. We don't know Okay, this is an angular momentum and it is proportional to the magnetic moment. Higher the angular momentum of the electron, higher will be the magnetic moment. So if an electron is in the L0 orbital, देखो, electron L0 orbital में है, what's the angular momentum? If an electron is in the S orbital, what's the angular momentum? Angular momentum क्या होगा? Zero होगा ना? क्योंकि L is equal to L into L plus 1 h bar. So when L is 0, this angular momentum is 0. आप क्लास में आते रहे हैं ना? So the angular momentum is 0. When the angular momentum is 0, the magnetic moment is 0. So an electron in the 1s orbital does not have any magnetic moment. But now we've entered the Schrodinger picture. क्योंकि Bohr's picture में तो orbitals नहीं थे. Schrodinger picture में आए थे orbitals or wave functions. Anyways, if we know the angular momentum, we can determine what the magnetic moment is. And this is a constant of proportionality. So the key idea that I would like to present is that whenever you have some angular momentum, associated with the angular momentum, there is a magnetic moment. Angular momentum L, magnetic moment mu, which is proportional to the angular momentum, and there is a constant of proportionality in between. अच्छा, ये तो होगी बोहर की picture. अब let's enter the Schrodinger world in which the electron is now a wave function and we have derived the orbitals, and we know that the magnitude of the angular momentum is quantized, and it's quantized according to this relationship. And we know that the z component is also quantized according to this relationship, NLH bar. Now, is this a vector quantity? Yes, the magnetic moment is a vector quantity. It points in a certain direction. It will have an x component and a y component and z component. If this angular momentum is quantized, will this be quantized? Yes. If the z projection is quantized, will this be quantized? Will the z projection of the magnetic moment be quantized? Yes. And what is easier to measure? The angular momentum or the magnetic moment? The magnetic moment is easier to measure, because you can place the magnetic moment inside a magnetic field and see how the magnetic moment interacts. And we look at that in a minute. So we can test the quantization of the angular momentum or its z component by testing the quantization of the magnetic moment or its z projection. So now we have a handle on how to test the space quantization idea. देखो space quantization की जो हमने बात की फ्राइडे वाले दिन बहुत काउंटर इंटुइटिव है. That is the angular moment. The physics does not give me any preference over one direction over the other. Classical physics does not give me any preference. You are in vacuum, there should be no difference between 30 degrees and 45 degrees, between 60 degrees and 93 degrees. All angles should be the same. But quantum mechanics tells us that angular momentum is quantized. The angular momentum can only point in certain directions. And these were the cones that we drew the other day. हमने cones बनाई थी for the angular momentum, right? So now the angular momentum is only pointing on this cone, because the angular momentum has now been quantized. So what's special with this angle? What's special with this angle? Why do we prefer one angle over the other? So this idea of space quantization is very counterintuitive if you think carefully. That is, one angle has some holy preference over another angle. Another angle is, angles in between these cones are not allowed for the angular momentum. Space quantization इतना आसान concept नहीं है समझना. That is why When Schrödinger presented his idea, Bohr did not believe it, Einstein did not believe it, Max Born did not believe it. The great quantum theorists of the time did not believe the idea of space quantization. They thought it's just a mathematical artifact, and there can be no experiment that tests space quantization, because space quantization is just an artificial mathematical artifact. It's just a mathematical convenience. It has no physical significance. But now we're going to discuss an experiment that actually shows space is quantized. That is, only certain directions for the angular momentum are allowed. And how can we test that? Because now we can measure the angular momentum indirectly by measuring the magnetic moment. Okay? Now if you look at this expression again, I have already mentioned that the magnitude of the magnetic moment must be quantized. You can put a minus sign here as well. L plus 1 H bar. So the magnetic moment has to be quantized because angular momentum is quantized. Likewise, the z projection of the magnetic moment is to be quantized. Minus E H bar 2m ml. Now these ideas come from the Schrödinger picture, remember, because Bohr had no idea of this quantum number, or his theory does not give. He had an idea, but they don't come out from his theory. This comes out from Schrödinger's equation, L and ml. So now we know, we predict that the z projection of the magnetic moment must be quantized. ठीक है? अच्छा, ये वाली जो quantity है ना, E over H bar over 2m. What is small m? ये mass of electron. This is the mass of an electron. This quantity, which I have written in a blue circle, is given a special name. इसकी dimensions क्या होंगी इस quantity की? बोलो, बताओ. चलो यूनिट्स बता दो. Amperes per meter square, amperes into meter square. Amperes meter square, area times current होता है ना. Because this is dimensionless, this is just a number, so it will have the same dimensions as the magnetic moment. This quantity is given a special name. It's called the Bohr magneton. Denoted by mu sub b, and its value is about 9.2 into 10 raised power minus 27 ampere meter square, I think, as far as I can remember. You can calculate the value of the Bohr magneton. अच्छा, electron है. Electron से छोटा. Is the electron a fundamental particle? Can you break the electron into smaller particles? No. There is no subelectronic world. Subatomic world होता है, प्रोटॉन के अंदर क्वार्क्स हैं, न्यूट्रॉन के अंदर क्वार्क्स हैं, लेकिन इलेक्ट्रॉन इज अ लेप्टॉन, इट्स अ फंडामेंटल पार्टिकल. You cannot break it up, which means, and you cannot have a, which means that, and the mass of the electron is very small. So this quantity is like a unit of magnetic moment, such as E is a unit of charge. The coulomb is a unit of charge. 1.6 into 10 to the minus 19 coulomb is the unit of charge. You can have fractional charge, by the way, in quarks and so on, but E is considered to be a unit of charge. It's a unit, and you count charges in units of the electron charge. The nucleus has a charge of 56 times the charge of an electron. So E is a unit of charge. Likewise, the Bohr magneton is a unit of magnetic moment. Okay? The Bohr magneton is like a unit of the magnetic moment. Alright. So let's now talk about an experiment, a classic experiment that demonstrated the magnetic moment is indeed quantized. And this experiment was performed by two German scientists, Stern and Gerlach. Around 1922. Both of them were German scientists, and I have uploaded on the website a very interesting historical account of this famous experiment. देखो अभी श्रोडिंगर की theory limelight में नहीं आई थी. Bohr's theory was very much there. It was presented in 1916. So these concepts of quantization of energies were there. The concept of orbits were there. And Bohr had already presented that the angular momentum is quantized. NVR is NH bar, right? This was Bohr's postulate. That is, the angular momentum is quantized. But he did not go beyond this postulate. And N takes the values 1, 2, 3 and so on. Look at one important difference. In the Schrodinger's model, the angular momentum can be 0. Whereas in the Bohr's model, the minimum value of the angular momentum is h bar. This is one important difference. In the Schrodinger's model, for an s orbital, the angular momentum can be 0. Whereas in the Bohr's model, the minimum value of this n is 1. So the minimum angular momentum an electron can possess is h bar. In the Bohr's model, an electron has to revolve around the nucleus because it's a different kind of model. It's based upon the motion of an electron around the nucleus. No. When you go to smaller energy, when you look at the electron atoms face to face, h bar is no longer a small quantity. देखो क्वांटम और क्लासिकल वर्ल्ड में फर्क ही है. If you're in the classical world, h bar is a small quantity, ignore it. You ignore quantization. But when you're looking at atoms face to face, you have the same dimensions, you have the same energy scale as an atom, then you cannot ignore h bar. H bar is no longer small. In the classical world, you can take h bar to be very small, or you can take the quantum number to be very large. This is the Bohr's correspondence principle. Anyways, so these are the ideas with which Stern and Gerlach started the experiment. Now Stern was a physical chemist. ये जो था ना, एक physical chemist था. ठीक है? Physical chemistry में इसकी PhD थी. और Gerlach was a physicist. अभी ताजा फर्स्ट वर्ल्ड वॉर खत्म हुई थी. ठीक है? Hitler was rising to power in Germany. So they were working under Hitler's rule, and both of them converged in Frankfurt. He was in one department and Gerlach was in another department, and Stern was a student of Max Born. मैक्स बॉन्ड की क्या कंट्रीब्यूशन है? मेजर कंट्रीब्यूशन बताओ, आप बताओ. मैक्स बॉन्ड की क्या कंट्रीब्यूशन है? एहसान फरामोशी नहीं करते. अब क्वांटम मैकेनिक्स पढ़े, उसका एहसान है हम पर मैक्स बॉन्ड का कोई ना कोई. आप बताओ, लास्ट रोज में से किसी को याद है? He interpreted the wave function. This is such a fundamental concept that Max Born interpreted the meaning of the wave function. Its modulus square gives the probability density. So Stern was a student of Max Born, or a postdoc with Max Born. Now Stern had an idea. He wanted to test the quantization of space. He wanted to test whether this theory is correct or not. So Stern thought that for n equals 1, which is the lowest state of the electron in the hydrogen atom, L can be plus h bar. L has to be plus h bar. But the electron can be moving clockwise or anti-clockwise. This is the Bohr's model. So the angular momentum can point in one direction or the other, upward direction or downward direction. So L could be plus minus h bar. He wanted to test the quantization of angular momentum. That is, the angular momentum can indeed point in only two directions, plus h bar or minus h bar. So this is something he wanted to test. bond discouraged him. यह स्पेस क्वांटाइजेशन तो एक सिर्फ हमारे ज़हन की एक पैदावार है, ज़हन का खलल है. Space quantization, there is nothing real about space quantization. It's just a figment in our mind. It's not physical. Max Born discouraged Stern. Niels Bohr discouraged Stern. Even Schrödinger discouraged Stern. But आहिस्ता आहिस्ता स्टर्न अपने आइडिया पर काम करता रहा. तो एक रात, बहुत सर्द रात थी. फ्रैंकफर्ट इज a very cold city if you know. तो स्टर्न उठते में, जब सुबह उठना चाहा उसने, तो अपने गर्म बिस्तर नहीं वो छोड़ सका. तो उसने बिस्तर में बैठ के एक्सपेरिमेंट का आइडिया सोचा. हम बिस्तर में बैठ के सो जाते हैं, लेकिन उसने एक एक्सपेरिमेंट का एक आइडिया सोचा और उसने गर्लैक से राब्ता किया. बिकॉज गर्लैक वाज एन एक्सपर्ट इन प्रोड्यूसिंग बीम्स ऑफ एटम्स, in atomic beams and molecular beams. So they thought of an experiment. All right. And what was the experiment? They made this experiment. अब फंडिंग भी बहुत कम थी, जंग के जमाने थे, जंग से उभरी थी जर्मनी, ठीक है, फंडिंग भी नहीं थी. तो उन्होंने ये किया कि उन्होंने बॉन्ड को कन्विंस किया कि तुम लेक्चर हॉल में बड़े लेक्चर हॉल में लेक्चर्स दो अपनी क्वांटम थ्योरी पर और उसकी एक टिकट रख दो. तो उस टिकट से उन्होंने कुछ पैसे जमा किए और ये एक्सपेरिमेंट बनाया. अब एक्सपेरिमेंट क्या था? The experiment worked as follows. A very simple experiment on the blackboard. It's not simple performing this experiment. There was an oven, and the oven I think was made of tungsten oven. Inside the oven they placed silver metal. And they heated this oven up to about 1000 degrees centigrade. So the sodium metal vaporized. Now we have sodium vapor inside the metal, inside the oven. Sorry, silver. ठीक है, सिल्वर एक सॉफ्ट मेटल होता है, सिल्वर कलर का होता है, ठीक है. तो उन्होंने टंगस्टन की ओवन के अंदर सिल्वर मेटल रखा और उसको वेपराइज किया, हीट किया ओवन को. एंड देयर वाज अ स्लिट इनसाइड द ओवन फ्रॉम व्हिच these energetic sodium atoms can emerge. Remember, this is not a molecule, this is just elemental sodium. Silver. Okay, this is elemental silver. So silver atoms can emerge from this slit and they move in straight lines. Some of them diverge. But outside the oven, they place two narrow slits, very narrow slits, so that a collimated beam of silver atoms can pass straight through. So now you have a beam of atoms, a beam of silver atoms. Remember, these are not molecules. Elemental sodium can exist on its own. So this is a beam of silver atoms. Now he passed this beam of silver atoms through an arrangement like this. Through a magnetic field, through the poles of a magnet. And the poles of the magnet were shaped in such a way that the magnetic field is non-uniform. This has a flat face, this pole has a flat face, but the upper pole does not have a flat face, it has a conical face. So this field is non-uniform. So we produce a non-uniform field. magnetic field. Question: what is the meaning of a non-uniform field? सिंपल इंग्लिश में बताओ, नॉन यूनिफॉर्म फील्ड का क्या मतलब? तो एक दूसरे के पैरेलल नहीं है, ठीक है? So a non-uniform field means the following: you have two, this is very important to understand, two magnet pole pieces. If those pole pieces are totally flat, then away from the edges the field lines will all be parallel and they will be perpendicular to the pole pieces, and the spacing of these field lines will be the same, because the number of field lines per unit area gives you the field strength. Away from the center, that is towards the edges, of course the field can be non-uniform. This is called the fringing effect. So in between the pole pieces the field is uniform. There is no variation in the field with x, y or z. It does not change with space. This is the meaning of a uniform field. But at the edges the field gets non-uniform. Now producing this non-uniform field is essential, and I will tell you why. Now after this silver beam, this atomic beam passed from the magnet, it impinged on a screen, which was just a glass slide. Alright. Now, what were Stern and Gerlach trying to show? They were trying to show that this angular momentum L is quantized according to Bohr's condition plus minus h bar, and therefore the magnetic moment mu must also be quantized, because if this quantity is quantized or if this quantity is quantized, mu should also be quantized. But which means that mu could be proportional to plus minus h bar. देखो ना, if L is plus h bar, mu will be proportional to plus h bar. If L is minus h bar, mu will be proportional to minus h bar. You get two values of the magnetic moment. Now why did we have a non-uniform magnetic field? Okay, it's very important to understand this. Let me ask you a question. You have an electric dipole, plus q minus q, and this is the electric dipole moment. P is equal to plus q r. This is separation, or the vector separating the two charges. You place this electric dipole inside a uniform electric field. The electric dipole is placed in a uniform electric field. What is the total force, net force acting on this electric dipole? What's the net force acting on the dipole? वहां बैक से बताएंगे. तो क्या फोर्स एक्ट होगी लिखते हैं. फोर्स नेट फोर्स इज वेरी, देखो बड़ा छोटा सा क्वेश्चन है, फर्स्ट फ्रेशमैन लेवल का क्वेश्चन है. मैं पूछ रहा हूँ नेट फोर्स क्या एक्ट होगी. सारे कह रहे हैं स्पिन कर देगा और वो टॉर्क है. Alright, so the net force acting on this dipole is 0. because there's a force acting like this plus F, and there's a force acting like this exactly equal in magnitude, opposite in sign, minus F. So the net force acting on this object is 0. However, I agree with you that this electric dipole will experience a torque. It will experience a torque, and the torque will act such that the final position of this electric dipole will align itself with the field. It will experience a torque, but torque does not mean a net force is acting on this dipole. And the torque will be given by the electric dipole moment cross product with the electric field. So torque will act, but no force will act, which means that this electric dipole will not experience any translational motion. However, if you make the electric field non-uniform, a denser field at the, and you place the same electric dipole here, a net force will indeed act on the dipole. Okay? And the net force will move this electric dipole in this particular direction, because the force on this charge is higher than the force on this charge, right? So this electric dipole will translate. So in order for a force to act on this electric dipole, a non-uniform electric field has to be present. Likewise, when you have a magnetic dipole, if you place a magnetic dipole inside a uniform field, no force will act. A force will only act on the magnetic dipole if you have a non-uniform field. Now how do I prove that? Suppose you have a magnetic field B. मैं आपको पहले बता दूं कि we'll take 5 minutes extra today. We have a field B. ठीक है? अब हमारे पास एक field है B, and you have a magnetic moment mu. Can I represent the magnetic moment by an arrow? Yes, because it's just a magnetic dipole, it's a vector. तो इसलिए magnetic dipole moments को arrow से भी जाहिर करते हैं. So this is mu, this is B. Now what is the energy of this dipole moment inside the field? When you have a magnetic dipole moment placed inside a magnetic field, can we find out what the energy of this dipole moment is? What's the preferred orientation of this dipole moment? It should align itself with the field. देखो अर्थ एक बहुत बड़ा मैग्नेट है. अगर आप कंपास लें, कंपास की नीडल will point in the north south direction, because that's the lowest energy configuration. Pointing away from in the opposite direction of the applied magnetic field costs you energy. Therefore, the energy is minimized when mu and B are parallel. So the energy is given by an expression. Does anyone remember what the expression is? It's the dot product of magnetic field and the magnetic moment with a minus sign. This is the potential energy or the magnetic potential energy of the magnetic dipole moment placed inside a magnetic field. जब ये zero, इनके दरमियान angle 0 है, then energy is minimum. When the angle is 180 degrees, the energy is maximum. In order to minimize energy, theta has to be 0. When theta is 180 degrees, the energy is maximum. So you have two configurations. This is the minimum energy configuration, and this is the maximum energy configuration. Minimum energy, and this is maximum energy. And in between you have energies that are in between. Simple classical concepts. Now when you have this energy of the magnetic dipole inside a magnetic field, We want to calculate the force that is acting on the dipole. Now how do we calculate the force from the potential energy? Again a question from mechanics. पोटेंशियल एनर्जी दी हुई है, हमने फोर्स फाइंड करती है. F is equal to minus x नहीं, आप 3 हो सकता है. ग्रेडियंट ऑपरेटर. अगर x ना हो 3 वन डायमेंशन में ना हो सिर्फ तो फिर क्या करें? dr थीटा फाई ग्रेडियंट ऑपरेटर है. डेल ऑपरेटर पढ़ा हुआ है ना? देखो ये these are not new concepts, these are concepts that you've already accustomed to, you've already learned, so we're now applying those concepts, nothing new. I'm going step by step. The force is just given by minus del acting on the energy E, इसे आप U भी कह रहे हैं, ठीक है? So this is the force minus del, what is the energy, minus mu dotted with B. Remember this is a scalar quantity, so now gradient operator is acting on a scalar quantity to give you a vector. ये एक scalar है, याद रहे. Right? Correct? Minus cancel हो गया. Now suppose that in this experiment, now we have to use the experimental arrangement. This is the x-axis, this is the y-axis, this is the z-axis. Let's suppose, in fact, this is what they did in the experiment. The magnetic field B points in the z direction. It points in the z direction. And it varies along the z-axis. It points in the z direction and varies along the z-axis. Which means if I draw a picture of the field, it looks like this. The arrangement is such that the field is maximum at one point, and as you go along z, the field diminishes. Which means that the field is pointing along, it only has a z component and it depends only on z. So, and it's pointing along the z direction. So this is the field. It only has a z component. This is the experimental arrangement, although it cannot be achieved with perfection for other reasons, but this is an approximate magnetic field that Stern and Gerlach applied, which means that this term is 0 and this term is 0 because Bx is 0 and By is 0. And what is this object? This object is simply iota partial x plus j partial y plus k partial z acting on mu z Bz, and this only depends upon z. Bz only depends upon z. Therefore, the derivative with respect to x will vanish, the derivative with respect to y will vanish, only this derivative will remain. So this is the force. The force turns out to be pointing in the k direction. Mu z is just a constant. I can write dBz over dz. So this is the force that is acting on the dipole. Okay? So this is the gradient of the field. Gradient का लफ्ज़ समझते हो? Gradient means the variation of the field with respect to a space coordinate. This is the field gradient. And the force is pointing along the z direction. So what are the possible values of mu z? Mu z can be positive or negative, right? Mu z can be positive or negative depending upon the direction of revolution of the electron. Which means that this force can point in the upward direction or in the downward direction. Which means that Stern and Gerlach expected that this beam will split up into two beams. One goes in the upward direction and the other beam goes in the downward direction. Because this beam of silver atoms has an equal mixture of magnetic moments of electrons revolving in clockwise direction or electrons revolving in the anti-clockwise direction. In other words, the magnetic moment mu could be positive or it could be negative. If it's positive, it gives force in the upward direction. If this is negative, it gives force in the downward direction. So this means that two kinds of forces are acting on the silver beams. There is a large number of atoms in the beam. Half of them will be deflected upward and half of them will be deflected downwards. And they should see two spots on the glass slide. Two distinct separate spots on the glass slide. However, it turned out that their experiment failed. ठीक है, their experiment really failed. तो अब हुआ ये, उन्होंने बार-बार experiment repeat किया, बार-बार experiment repeat किया. They were so convinced that they should get the result which Bohr had predicted, that is the quantization of the angular momentum, that they kept on trying, but they were always failing. So तो फिर क्या हुआ? फिर ये हुआ कि Stern changed his university. He went from Frankfurt to Gutenberg, and Gerlach visited him in Gutenberg. And then Gerlach wanted to come back to Frankfurt, but he missed the train. So he stayed for another day, and they kept on discussing how to make this experiment work. Then they set up the experiment for another time, and it failed again. And they were very frustrated. So Stern was a chain smoker. And academics do not get paid well enough. So he used to smoke bad cigars, cheap cigars. और ऐसे सिगार जिनका धुआं बहुत सल्फरस होता है. तो एक्सपेरिमेंट के पास वो अपनी ग्लास स्लाइड को देख रहे थे, तो साथ साथ स्मोक कर रहा था. तो अचानक उन्होंने देखा कि ग्लास स्लाइड पे वक्त के साथ साथ as he kept on smoking, two distinct spots started appearing. Now what was really happening is that the smoke was sulfurous. The smoke had sulfur in it. That's what a bad cigar, I have never smoked, but that's what I heard. A bad cigar or a bad cigarette has a sulfurous smoke. So when this silver reacted with the sulfur, it produced silver sulfide. I think this is silver sulfide. It produced silver sulfide. And silver sulfide has a distinct black color. In fact, this is how you develop photographic films in the past. So, and they were surprised, and of course they were delighted to see these distinct spots. And this is how they showed that two distinct spots are formed. The magnetic moment has to be quantized in accordance with the Bohr's principle, in accordance with the Bohr's quantization of the angular momentum. So they reached this beautiful result. This experiment was again performed in 1925 again, and instead of using silver atoms, they used hydrogen atoms. It was again repeated with sodium atoms. So a large number of experiments were performed with different elements, and two distinct spots were observed. But the problem is, if you look carefully enough, Stern and Gerlach had showed the quantization of angular momentum, but their interpretation was incorrect. Why was their interpretation incorrect? Because Schrödinger's theory had come into action, and the Schrödinger's theory gave you the orbitals. Now if you consider the hydrogen atom, what's the ground state for the electron in the hydrogen atom? 1s. And what is the angular momentum, small l, for the s orbital? 0. What is the magnitude of the angular momentum? 0. What should be the magnetic moment? 0. Therefore no splitting should be observed. Let's look at the sodium atoms. The valence electron of the sodium atom is in the 3s orbital. Okay, 3s1 is the valence electron of the sodium atom. So all the sodium atoms that are inside this being there in the ground state, 3s है ना, hydrogen helium 3s है, 3s1. So L is 0, and capital L is 0, mu should be 0. You should not see any splitting. तो स्टर्न और गर्लाच ने इतनी मेहनत से जो स्प्लिटिंग ऑब्जर्व की थी, now they had to explain it, because even for a silver atom, the valence electron is in the 5s orbital. Again, mu should be 0. Therefore, no splitting should be observed. तो स्टर्न और गर्लाच ने बोहर की क्वांटाइजेशन, बोहर पोस्टुलेट को सेटिस्फाई करने के लिए इतनी मेहनत से जो स्प्लिटिंग ऑब्जर्व की थी, now they were in a fix. How do we explain this splitting? But this splitting existed. Now this led to the concept of another property of an electron, which has nothing to do with the orbital angular momentum. Okay? And this led to the prediction of another property of the electron called the spin. Now what is the spin of an electron? The spin of an electron is a fundamental property of the electron. Last 5 minutes of the class, please bear with me. You put an electron on a balance, on a weighing balance, it will give you a mass. It will give you a mass. You measure the charge, you can measure the charge on electron through electrolysis or through a electron deflection experiment in a charge to mass ratio fashion. You can find the charge on an electron. So these are fundamental properties of the electron. The charge on an electron, the mass of an electron. They don't come from Schrödinger's theory. Okay? They come from some other string theory or some other more exotic theory. But these are fundamental properties of the electron. There is a third property of the electron, which is called the spin, denoted by S. ठीक है, ये एक तीसरी प्रॉपर्टी इलेक्ट्रॉन की स्पिन, और इसको जाहिर करते हैं स्मॉल s से. This is a warning from the attenders at the class session. So this small s for an electron takes a value 1/2. and we say that the electron is a spin half particle. It's a spin quantum number. It's a spin quantum number with a small s equal to half. And the spin angular momentum, हमारे पास एक orbital angular momentum था capital L. We also have a spin angular momentum, which is given by small s into s plus 1 under root h bar. Since small s is half, this turns out to be under root 3 over 2 h bar. So this spin angular momentum, this is now spin angular momentum. Can only have a fixed magnitude, which is under root 3 by 2 h bar. And the z projection of this spin angular momentum is given by ms h bar. जिस तरह orbital angular momentum and l h bar था, spin angular momentum z projection is ms h bar. And what value can ms take? Ms takes the values plus half and minus half. जिस तरह analogy, ml takes the values l minus 1, l minus 2, all the way up to minus l. ms takes the value s minus 1, all the way up to minus s. But since s is half, ms can only take up two values, plus half and minus half. So now if you look at this expression, let's look at this expression. There is an orbital angular momentum and associated with it is a magnetic moment. So I write a small l here to tell that this magnetic moment is associated with the orbital motion or with the orbital angular momentum. I can write a similar equation for the magnetic moment associated with the spin angular momentum. इसी के analogous, provided I write a small constant here, g. So I will explain this further on Friday. A few announcements. On Friday, we're going to have a very important lecture and a quiz. Okay, I'm going to build upon this concept. And I'm going to also do one or two short problems. So be there on Friday and revise all of what I've done today. And what I would like you to think about is, if this spin angular momentum is quantized, how do you explain the results of the Stern-Gerlach experiment? So please be there on Friday. It's going to be a very important session.